Someone was going up it. But that's like a joke in like
Oh shit.
it's a euphemism. Going to Belize is like when someone retires, they go to Belize, but it's also like if you kill someone,
Right.
send it to Belize.
Okay.
Cool. So I'd like to welcome you all quickly to what's probably going to be the final lunch talk before September, being delivered by our very own infidel Babbitt. And the infidel has straight over whenever you're ready.
Thank you. So I'm going to be talking about a topic in cosmology known as the Hubble tension and the possibility that this is caused by our location in a large local void. So here's some papers related to this idea and some search that you can put in order to find out a little bit more. This will also be my final talk as a postdoc here. So I'd like to thank everyone who's helped me over the last decade or so. I'll be moving to Portsmouth next, if anyone interested to work on this idea in more detail. What is the Hubble tension, which we heard of? The Hubble tension is about the present expansion rate of the universe. So the standard cosmological paradigm known as lambda full dot macro, ΛCDM, has achieved many successes over the years and decades, like the nucleosynthesis in the very early universe, the first few minutes, galaxy cluster mass function, very late times. So what usually people do is they calibrate the parameters of the ΛCDM model using the anisotropies in the cosmic microwave background radiation, which was emitted around 400,000 years after the Big Bang. So it's very ancient light. In fact, it's the most ancient sort of light you can see. And it's been redshifted into the microwave portion of the spectrum. If you apply the ΛCDM model to the CMB and you try to fit the CMB, you could get the present expansion rate. So a dot is the derivative with respect to time, and A is the scale factor of the universe, which is 1 today by convention. So if it's half at a certain epoch, that means the universe was half current size at that epoch, roughly speaking. So this is what the CMB looks like, as you probably know. The temperature fluctuations on different angular scales are plotted here. I've kind of shown them overlaid on the CMB so you understand that it comes more or less directly from the CMB map. It's essentially just like a Fourier transform effectively in angular coordinates, multiple expansion. Okay, so that's the early universe route to get the H naught. Obviously, this requires the use of a cosmological model. Now, because this is at very early times, it's not actually that you're measuring the present expansion rate by looking at the CMB. But you can also try to get H naught in a different way. If you look at nearby objects, especially galaxies, what we see is a nearly linear relation between distance and the redshift Z, which is defined in this way. So if you see a spectral line, you know the rest frame wavelength, you know what wavelength you observe it at. This is the redshift. And what we think is going on is that as you look at more and more distant objects, you're looking at them further back in time. And the scale factor A has increased during that time. And what should happen is the wavelength should rise proportionally to the scale factor A. So there should be some redshift due to this cosmic expansion over the light travel time. If you were to then basically find the speed of light times the redshift gradient, that should tell you H naught. That, of course, should be the same numerically as the H naught you get from looking at the CMB. which would be a very stringent test of the ΛCDM model. But unfortunately, it fails this test. So what I mean by that is evident in this graph, which is actually a compilation of many different results. It's a very recent one. Above the line, things from the early universe and CMB, so that corresponds to this part. And below the line, late universe measures with different blocks representing this different sort of types of objects used to measure the distance. Redshifts were very much easy to obtain. So typically the conquest around the distance. But you can see that all the different measures more or less agree. Okay, so that's the Hubble tension. Now, one way to try and get around to try and find out who's actually correct here is to look at the age of the universe, which is inversely proportional to its expansion rate. The faster it's expanding, the younger it must be. Now, what has been done recently is 11 carefully chosen old objects were used by Chimati Morisco to find like the age of the universe. But it tells you really the age of these objects. You have to add a small amount on top for how long it took them to form after the Big Bang. To convert an age to an H naught, you also need to know the matter density, but you could do that independently of the CMB. You can ask if you like it, how that's done, but that's the reference, and it can be done with very little uncertainty. So that doesn't really affect the H naught estimate. So what actually does this look like? Well, if you have on the x-axis the time needed for these objects to form, and on the y-axis the H naught, this is the famous Hubble tension. This is the local value. This is the CMB value. And these points show the age of the universe converted into an H naught value. So the age of the universe is this many gigayear plus an extra 0.2 gigayear formation time for those objects with a factor of 2 uncertainty in it, pretty broad. So this is basically the value of H naught, but it could be down here, and then you would be able to have a slightly higher H naught. Or if you had assumed objects form very slowly, then H naught could be a bit lower. But you could see though that this is strongly favoring the Planck value of H naught. What this means is that ultimately the Planck H naught is correct, and the local redshift gradient dz by dr somehow has been inflated. So how might that have been? Clearly, that requires some sort of local phenomenon. What has happened, in my opinion, is a local structure. This is not super controversial as such to suggest that local structure affects the local H naught to some extent, because obviously you have velocity, you have so-called peculiar velocities, which are velocities on top of the cosmic expansion. So, for example, the Andromeda galaxy is approaching us. That's what we see, not because the universe is contracting. This is a peculiar velocity. Peculiar velocities should become less important as you look at more distant galaxies, not because the velocities are any slower, but because there's more redshift from cosmic expansion. So in relative terms, the impact of peculiar velocities should decrease. However, if we are located near the center of a large void, which is kind of what we've tried to show in this illustration, then you get outflow from the void, and you could have a situation where the outflow velocity is kind of zero, exactly the void center, then rises as you go further out. And only as you go like much further out to the regions which are no longer in the void does the peculiar velocity drop down to zero again. So you could get like an extra gradient to the redshift against distance because of a term related to the d Beck by dr. And that could skew the local H naught. This certainly is not inherently very controversial. So what is controversial? I'll get on to it in a sec. The other thing to bear in mind is that there's a lot of evidence for this scenario in terms of the so-called Keenan Cowie or KBC void, which roughly speaking, it looks like this. So here what's plotted is the luminosity density. Don't worry about the exact values on the y-axis, but that's plotted as a function of the distance. And you can see that it sort of rises and then goes flat. What we think is going on, this flat level is the homogeneous value for the universe. That's the average luminosity density of the universe at late times. The average covering luminosity density. But locally, we're in some sort of a hole or a void. So what we were doing in the study, which we'll talk about in a sec, is we're using this point, which is an average over this region, and also assuming that this level is the average for the universe as a whole. So in case you're wondering, like, how much of the galaxy luminosity function was used to get these observations, that's shown on the left. So you can see that most of the skies covers up to this limit, and then a lot of it also, some of the fields cover down to here. So the majority of the galaxy luminosity function is used for these results. There's a more recent study from Wong et al. 2022, which comes to similar sort of conclusions, though it only goes out to about here approximately. So it's only kind of able to probe the rising part and not really the flat part of the curve shown here. Okay, so the KVC void cannot be understood in the ΛCDM framework. We looked at a grid of 1 million vantage points in MXXL. We looked at regions for each observer within 40 to 300 megaparsec, found the total mass in halos, the total stellar mass, I should say, using a semi-analytic approach because it's your N body. We compare the density to the cosmic mean value, so basically repeating this exercise but for the whole box. Then there's a certain redshift space distortion effect, which I'll explain later. But basically, this is because observers think they're seeing out to some distance d based on the redshift, but they're actually looking out to a smaller distance because the local Hubble constant is larger in a void. So therefore, they see fewer galaxies, which tends to make the impact of a void more pronounced. It looks more underdense than it actually is. Anyway, that leads to a 1.5-fold enhancement in the density contrast in ΛCDM. So in ΛCDM, the density contrasts look like this. Delta is the underdensity, and obviously it's 0 on average, but you could get some underdensity, you could get overdensity as well. Now, the density case is more important for us, but you can't get to the observed underdensity, which is 46 plus minus 6%. There is a 6 sigma tension. One thing we looked at is, of course, if you were in an underdensity, that would inflate the local Hubble constant. So if we plot the apparent underdensity on the y-axis and the ratio of the local to the global, that background H0 on the x-axis, what you get is something like this. So this green point is the sort of blank value, if you like, the background cosmology. There's no underdensity on average. The local and global H0 are in agreement. If you're in a void, you would sort of move along this track in ΛCDM. But even at 5 sigma, you'd only get up to this point. Whereas the observations are up here with their error ellipses. So what this is suggesting, though, interestingly, is that if you had a lot of cosmic variance, more than in ΛCDM, such that instead of being a 10 sigma fluctuation, this point was perhaps only like a 3 sigma event, then you could simultaneously explain the underdensity that we observe and the Hubble tension. So of course, this loop track might go differently in other theories, but the point is approximately you could hope to solve the Hubble tension and the KVC void simultaneously. So what we did to try and simulate this is we enhanced the strength of gravity by using the so-called MOND or main gravity dynamics theory. So this is all standard physics. If what you do is you evolve the trajectory of a particle, the acceleration having this term, which is what you get in a homogeneous expanding universe, plus an extra term due to the void. This is the initial velocity. It's on the Hubble flow initially. The acceleration, of course, is not purely the cosmic acceleration term, but there's also an extra term due to the void. What you need to do for that is find out, like, interior to the radius of the particle's trajectory, how much less mass there is than if the universe were homogeneous. That's the delta M term, where delta M is like this. So that's the mass there would be in a homogeneous universe, and this is the mass enclosed interior to the particle's trajectory, which stays constant as you do the integration. But this obviously doesn't. So then that leads to an anti-gravitational effect. In MOND, what we do is we, instead of using Gn up here, we use G, where G is like Gn times an enhancement factor. So this is just a sort of a way to enhance the strength of gravity, which you need to do in order to form something like the KBC void. Now, what does that do? Basically, what it does is if you plot the density contrast on a 300 Coulomb parsec scale as a function of the cosmic scale factor 8, so this is basically almost linearly proportional to the time, more or less. So you can read this as time divided by the present date, if you wish. What happens then is in the ΛCDM model, you get this sort of red line, or this line if you start with a much deeper initial underdensity. While in MOND, you get these blue lines, depending on the exact assumptions. You can see that in MOND, of course, structure will grow much faster. Also, because for the same delta today, the time derivative would be higher in MOND, which means that the same density contrast today is associated with larger peculiar velocity, which, roughly speaking, means that the blue line in MOND would be further to the right, or kind of be like that instead, roughly speaking. That will depend on the exact details of the gravity theory. Now, the other thing which I've already alluded to is that redshifts are not purely cosmological anymore. Well, they never really were. We know there's other sources of redshift. So the ratio between the observed wavelength of a photon and the wavelength it had when it was emitted includes the usual factor from cosmic expansion. So this one actually is the value of A today, like I mentioned. There's a Doppler effect, and there's a gravitational redshift or GR effect. What we did to try and quantify what is going on is we looked at the delta A, which is the difference between A and A app, where the A app is the apparent A that would arise if you basically only consider this bit of the equation. You ignore the Doppler and GR terms. In other words, you looked at the redshift, you found out A from that. This is not exactly correct because redshift is not only due to cosmic expansion. But if you assumed it was, you'd be able to get some value of A app. And in our model, we know the actual value of A. So you can look at the delta A, and then you can take its time derivative, which will obviously be related to the H naught. So what we did is we plotted, like in a joint sense, H naught and the Q naught bar, which is the so-called cosmic acceleration parameter related to the second time derivative of A. Okay, so at late times A is equal to 1. What comes in here for an observer is the apparent A dot and the apparent A double dot, rather than the true background values. So what locally people do is they get these using supernovae in this sort of local redshift range, use the second order Taylor expansion AFT. We get model predictions. Basically, we find out how much A double dot and A dot are higher than the background values, and we add them onto the background values. So what you get is something like this. So H naught and Q naught bar should be here, based on looking at the CMB. They're actually over here, if you look at the local data, with these sort of error ellipses slightly tilted, the observations therefore are in serious disagreement with the model. Well, that's the ΛCDM model without any local void. What about our special void model? Well, we tried 3 different density profiles. One of them obviously worked pretty well. The other 2 actually kind of overlap here. Both profiles are here, and that also worked pretty well. What is in our model? Well, we have basically a void. We have outflow from the void, plus we have a systemic void velocity due to understructures in the universe. It's important for some of our calculations the whole void should be moving. What we did is we divide the void into cells. We found the CMB frame velocity in each cell. Using the cosine rule, there's outflow from the void plus systemic velocity, which we add as vectors. And roughly speaking, these red cells are meant to illustrate the part of the void in which the peculiar velocity is consistent with the observed peculiar velocity of ourselves, of the local group of galaxies, the Milky Way and Andromeda. So basically, our local, a very local region of the universe. So this is just an illustration, but this kind of shows what it would actually look like in a model. The first thing to realize, these colors show the velocity of the CMB frame. The velocities are axisymmetric on the x-axis. So I'm going to show a single semicircle. The black contour shows the locus of points where the peculiar velocity matches the observed 627 kilometers a second. We need to show on the black contour, which isn't that unusual. I mean, if you try to argue that only a small fraction of the void is within the black contour, that's true, but that's about 2% of the void volume. So our position in the void is not that fine-tuned. Okay. Now, we in the Haslbauer 2020 paper, we looked at several other things, and we argued that basically we managed to fit that constraint, but a bunch of other constraints as well, with an overall tension equivalent to about 2.5 sigma. So that includes various other things related to the local Hubble diagram and the galaxy number counts. So it fit pretty well. But we have some additional recent constraints, which I explained some detail in my last talk. So I'll cover them briefly here. But basically, you can test the void model using the velocity field within a few hundred megaparsecs. As you can see, we've got like predictions. The main problem is that redshifts are due to expansion of the universe and also like velocities on top of the expansion, the peculiar velocities. So these are hard to disentangle, but it's inevitable that we would be somewhat off-center in a local void. So the apparent expansion rate would depend on the direction to some extent. So what we did, we are doing additional work on this issue using supernova traces. But what I want to explain is we got some crucial results regarding using galaxies as traces, which have been covered in New Scientist article, this conversation article, and also in this Astrobike, which was written completely independently of me, unlike these two. What is the bulk flow? Well, the bulk flow is basically the average velocity of a sphere centered on our location. You do find this out by looking at all the galaxies in it, of course, as much as you can. Trying to fill in the blanks for any regions like obscured by the galactic disk by extrapolating other regions, things like that. What you can see on here, so this is just to recap the void velocity field. We considered 2 locations for ourselves in the void. So we have to do this black contour, but we considered just the inner vantage point to be on the x-axis, like where the contour intersects, and here and here. So there's like inner and outer vantage points, and also 3 different void density profiles. So what we did is, show all these results. I'll discuss the gray lines on the next slide, so don't worry about that. But what we found for the outer vantage point with these dotted curves, that doesn't work. Okay, that doesn't fit the data. With the inner vantage point, with these solid curves, they do track the data, but they don't quite fit it. What you'd ideally like is to boost the curves up somehow. And that actually is not very unreasonable. The reason it's not, the reason it's a plausible thing to do is because we were constraining our location of the void based on the velocity of the local group in the CMB frame. So this is just a mean-squared Andromeda, remember, so on a scale of about 1 megaparsec, which will be affected by other nearby galaxies, maybe 2 or 3 megaparsec away. This kind of small-scale structure obviously is not included in our large sort of void flow model or outflow model. So the local group velocity, is affected by these small-scale motions. So what you'd ideally want to do is get the average velocity on a scale which is much larger than galactic separation, so larger than like 1 megaparsec, but much smaller than sort of the 300 megaparsec scale of the void. What we did therefore is we borrowed data from Watkins et al. On a scale of 50 inverse H megaparsec, and used that to set a location instead. So Watkins kindly lent us 2 additional data points here, and you can basically see that so what the bulk figure on the y-axis is because of projection effects only measuring 1/3 of the actual velocity. So what you can see, because it's going up to around 280 kilometers a second, is that really the local region of the universe moving with respect to the CMB by about 840 kilometers a second rather than 630. That means we should be on this gray contour instead of the black one, which means that the inner vantage point would shift slightly towards the void center and the outer one slightly away. But as we already seen, the outer vantage points don't work. So look at the inner vantage point. Moving that slightly closer to the void center, you would have this gray curve. Now, you could argue, and it's obviously correct, that these gray curves, because we've chosen our location of the void, is guaranteed to fit this first point, but it's not guaranteed to fit the rest of the curve. However, our models do nonetheless fit the rest of the curve. So 2 out of the 6 models we kind of considered a priori would be reasonable to fit the observations. So that's a bulk flow success of our model. And this is indeed a great success story, also in terms of the outreach. But that's not really what I wanted to bring you all here to explain, because I explained all this just a few months ago. What I wanted to explain, there's some crucial additional results that have been obtained since then. The first thing is that, well, if you were to try and infer the H naught from data in some narrow redshift range, you have to make some assumptions, of course, on exactly how you do that, right? But that's kind of what we'll do in the CMB as well, obviously. That's like H naught of Z equals 1100. But if you were to try and do that, what should happen in any local solution to the Hubble tension is that you recover the Planck value of H naught once you start looking at higher redshift. Because obviously in such a model, the Hubble tension is a local effect. So what we made 3 different assumptions of how exactly you're supposed to get H naught from data at high redshift. And yeah, they don't really differ very much. But what we've shown here is a method, which we call method 3 in the article, is most comparable to the observational study. So what shown here, these solid curves show the void model. The green model we explained earlier didn't work very well with the bulk flow results, but the red and blue models really should be what you are looking at. And not the dashed red one either. That's just an illustration of what happens if you neglect the gravitational redshifting effect of our location on a potential hill, and how photons have to lose energy reaching us. So these red and blue curves, which are similar to each other, more or less do fit the observations, which incidentally do show like a decline from the high local value down to the Planck value. Okay, especially the more recent data, which is shown in black, as opposed to the slightly earlier data in gray. But anyway, the model seems to track between the two. So if you imagine that observation went from here to here, and then they'll eventually settle down somewhere in the middle, what usually happens. Then you can see that our model was indeed pretty good. Not to mention that the fact that it declines down to the Planck value is quite remarkable. It's not at all guaranteed to do that. Famously, the local supernova data do not match the Planck value. Right. So the other thing that I did with bachelor student Ellie Gurini is do a special analysis of supernovae, basically assuming the Hubble parameter is the is what happens in a Planck cosmology. So this is not H naught, but it's the actual value of H, which is A dot over A. But we've added an extra adjustment to mimic the effect of a local void. We also added a chi-square penalty based on the age of the universe, but without worrying about this term, because that we think is arising from outflow from a void, not reflective. It's not a reflection of the actual value of A dot, and therefore it doesn't come into the age of the universe. And that's for the nominal assumption that the objects these people saw formed 200 mega year after the Big Bang. So what you can see here in terms of the inference on these parameters, so this is plotted with pi GPC, also called giant triangle Cartesiogram, is the inference. So basically 1, 2, and about 2.6 sigma contours. And this red dot shows basically what you would expect in a void model, roughly speaking. I mean, of course, roughly speaking, you would expect the omega m to be about 0.31 because you should be consistent with the Planck cosmology. The H naught should be about 67. The omega H naught, so the delta H naught should be about 7 because we know that locally H naught is about 7 kilometers a second megaparsec higher than the Planck value, about 74 instead of 67. So that's basically what I've shown with these red dots. You can see that it's roughly consistent with the observation. In other words, the observations do allow a local void sort of solution to the Hubble tension of this kind of form. So what about the thing that I advertised at the start, the baryon acoustic oscillations? So this is quite critical. The baryon acoustic oscillations, in case you're not familiar with them, are basically imprinted in the very early universe. So I remember I was showing the CMB and its power spectrum earlier. There's a characteristic scale imprinted on the CMB, which is the sound horizon at the time of recombination. How far could a sound wave travel until hydrogen atoms, new hydrogen atoms became able to form? Now, this angular scale is imprinted on the large scale distribution of matter at that time, and therefore at late times, it's also visible in the galaxy distribution. So you can actually see an imprint of this today. And roughly speaking, the large scale distribution of galaxies looks like this. Okay, that's obviously been exaggerated, but you can see that there's a certain characteristic length scale. And what it actually looks like is if you were to plot the galaxy correlation function as a function of separation, so how likely two galaxies are to have a certain separation. Ideally, what you would do is find all pairs of galaxies and plot all the pairwise distances of a histogram. But what you would get is the curves which sort of look like this. So there's some kind of a smooth decline, but there's a special bump here, which is called the BAO bump. So that obviously corresponds to a certain angle on the sky, if you like. So what do we actually see when we look at BAO observables? When people talk about BAOs, what are they observing? There's two things they're observing: the angular scale of the BAO feature and the redshift depth. This is because you can orient the ruler orthogonally to your line of sight, it will subtend some angle on the sky. You can also orient it parallel to a line of sight, in which case it will be a redshift depth. I'll explain that in a little more detail. Here, what's plotted out is the separation along the line of sight and the separation orthogonally to the line of sight. So we're in the plane of the sky, and the color shows the strength of the correlation function. Dividing out, I think, like a smooth polynomial fit. And you can see this special ring-like feature, which is the BAO feature. The angle, delta theta, is the length of the ruler divided by the distance, and you are in the ruler parallel to the line of sight. What you do instead, you get a redshift depth, which is basically because line from the far end of the ruler must be emitted earlier to reach out now, and therefore the universe is smaller then. So it must have expanded more. The line from the far end of the ruler is redshifted more. A void will raise the redshift at fixed look-back time, fixed DC, but the exact relation, so that will alter the exact relation between redshift and DC to then alter how delta theta of Z works, like what it looks like. The first thing we'll look at is the results. The results of comparison between the angular scale of the BAO and the expectation in ΛCDM for fixed redshift. That's shown as this so-called alpha perpendicular parameter of the y-axis. Technically, you're not able to measure DC directly because you measure an angle, so that's DC over RD. But you can assume the BAO ruler length is coming from the CMB. And that has a very small uncertainty. So that contributes to a small systematic uncertainty. What we've done, obviously, by dividing on the ΛCDM values, that's made it pretty simple what you're supposed to get without a local void. Assuming the Planck background cosmology, it should all be flat line at 1. The measurements are shown in different colors for different surveys, different marker sizes for the year of publication. Earlier results are shown with smaller points because we think the more recent results are more reliable. The models that work best are again these solid red and blue lines. The dashed versions show what happens if you neglect the gravitational redshift effect. What you can see here, roughly speaking, most of the points are below the Planck value, the void-free value. So red and blue lines do put that thing like that. That's because of the handful scale. Now, regarding the redshift length of the BAO, that measures without a local void. That measures the expansion of the universe in the time it took for light to cross the BAO ruler. Okay, but that's without a void. If there was a void, that would certainly be important, but you'd also have an additional effect. Well, first of all, there'd be an effect from the change in the void over time, but that's a very small effect. The main effect you would have is that at the far end of the ruler, you're further out in the void, where the velocity is different because the void has the whole velocity structure. Obviously, not exactly the same velocity everywhere. Remember, BAO measurements are typically quite far out, so you're looking at a regime where the void outflow velocity is decreasing as you go further out. But what happened with the BAO results for based on the redshift depth? So that's the so-called alpha parallel parameter. And here you can see that because we rounded some data at low redshift, it becomes difficult to say whether a void is preferred here. One thing that is even less good from an observational point of view is to look at the so-called alpha Klaczynski test, where you take the ratio of the previous two graphs, basically. That completely removes sensitivity to the length of the BAO ruler. It's cancelled out by doing this. But it also raises the uncertainties, as you can imagine, because you're taking the ratio of two quantities. So in logarithmic terms, you've subtracted one from the other. And this also reduces the void effect because the void affects the two in a similar sort of way. Not exactly the same, but in a similar way. So that reduces the signal. Obviously, this leads to a drastic loss of the signal to noise ratio you might hope to achieve, which means that looking at the alpha Krasinski test doesn't unfortunately tell us anything yet. But one thing that is one way of looking at the data which reduces the uncertainties is to look at the so-called isotropic average distance measure dV, which is basically if you combine the previous graphs instead, but weighting the angular determination like twice as heavily as the line of sight determination, because there's two dimensions of bigger this time, only one parallel to the line of sight. You can get this so-called dV, and you can plot, of course, the ratio of dV, like that observers report to the dV in the ΛCDM model, assuming no void. And you can also plot what should happen with our void model. So, of course, like by definition, in the Planck cosmology, without a void, you'd be on this line at 1. With the void model, you should be on the red or blue lines instead. And here you can see that definitely a local void did improve the fit to the observations. One important reason is because there's more observation. Like a lot of papers only report dV because it's much easier to obtain than like the DC or the DH. But anyway, you can see that this hasn't fit all the data perfectly, but it's worked better than assuming it's like solid line at horizontal line at 1. You can ask me more about like exactly what's on here if you want, but basically the circular points weren't on the previous graphs because they whereas the diamonds were essentially. So there's some new results on this graph which weren't on the previous. Yeah, so that's the BA results. And since I have a few minutes, I'll just explain one thing quickly before I get to the conclusions, which is, so I want to provide a brief update regarding some claims that MOND works better than Newtonian mechanics in local wide binaries, which are a strong test of MOND. So these are stars separated by about 10,000 astronomical units approximately in the solar neighborhood, so within about 300 parsec. Now, some researchers have claimed that wide binaries favor MOND, but we have found that there was a fatal flaw in the quality cards they used for their sample. That's shown in the first row, where what's shown here, the yellow is a distribution of a parameter known as beta, which is basically the velocity divided by the Newtonian circular velocity. And that, so that's shown in yellow. The red line is the Newtonian, sorry, the red line is the MOND prediction, the blue line is the Newtonian prediction. And the first column shows quite low separations. So this is the separation in the plane of the sky divided by the MOND radius. You don't really expect any kind of MOND signal in these two columns. In this column, you should be able to distinguish Newton from MOND. So the third column is really the critical one. Now you can see that it does look a bit more like MOND in this column, with this sample. And these values written here show a Kolmogorov-Smirnov test applied to the observed distribution comparing it to the simulated one. The p-value for the Newtonian case is very small, while for MOND it's reasonable. This suggests that MOND is favored. But as I was saying, the first row suffers from fatal quality card error, which I explain in some detail in my paper. What about the more recent samples from J 2024, which was a very recent study, sort of the latest that Keenan has come up with? Here you can see in these panels, in these rows, the two new samples. The bottom row should be a bit cleaner, but it has like a smaller sample size. What's happened here? So again, you can't really distinguish Newton from MOND in the first two columns. In this one, it should be clear that the blue Newtonian model has fit way better. Of course, those authors are always going to come up with some way to make it look relatively better for MOND. But what actually happened is that the test statistic for the Newtonian case is about 4% or something like. And apparently there was a 40% error on that as well. So it could have been as high as 0.18. Clearly, that's not sufficient to exclude Newtonian mechanics. You're not going to throw away Einstein's theory of gravity on the basis of a p-value of 0.0. I mean, so that's with this sample. With this sample, it was 0.08. That's probably just because it's a smaller sample. But in any case, it should be clear also in this row that the data is a bit noisier, but the blue Newtonian line has fit better than the red MOND line. So MOND doesn't actually work in local wide-band rings. A conclusion you can also obtain from solar system ephemerides. So yeah, that's the conclusion. There's also been like a failure in clusters, which I won't go into just now. Okay, so now to conclude, the observations of galaxy number counts in different redshift ranges locally, where we can see the majority of the galaxy luminosity function. You can't do that further out. That shows that we are in a significant underdensity out to approximately 1 billion light years. There is good evidence across the whole spectrum, from radio to X-rays for this. But you can also look at the CMB and see that the initial conditions of the universe were quite homogeneous. So clearly this void formed over time, which means there must have been significant outflow to empty this region out. So based on that argument, you can kind of guess that the local H0 should have been like maybe about 10% higher than the average value, which it is actually. Now, that allowed us to link the Hubble and local void tensions for ΛCDM in a semi-analytic study. The local void I was talking about cannot arise in ΛCDM, unfortunately. But you can link the Hubble and void tensions for ΛCDM in the semi-analytic void model, or you can assume they're independent flukes, which seems very unlikely at this point. But they would really need to be independent. They measure it in quite different ways. For example, the assumed value of H0 doesn't affect this result. Also, another thing that we did is predict the bulk flow curve using this model. We predicted it and it was observed. The other thing I wanted to mention is that the ages of old objects in the galactic halo, converted using a value for omega f that doesn't come from the CMB, by the way. It indicates a high local, it indicates a relatively high age, which is consistent with basically the Planck H0, but not with the 8% or so lower age you would need in cosmologies that adopt the high local H0 as the actual value of H0. So the ages of these old objects tell you that the Planck H0 is essentially the right value at the background level. Ultimately, A dot today is equal to the Planck H0. That means the locally high gradient of redshift with respect to distance must be due to an approximately 10% level contribution to the redshift that doesn't come from the expansion of the universe. It comes from something else. Okay. There have been various controversial proposals for what that might be. Just time light hypotheses. I was recently answering a question about that could be what this is. But the most conventional sort of explanation is that it's just peculiar velocities, because we know that these things obviously exist and contribute maybe 1 or 2% in ΛCDM, but not this much. However, if you're able to adjust that ΔCDM slightly, maybe this would be possible. If you infer H0 from data at high redshift, so beyond about 0.5, you recover the Planck value of H0. It's only the low redshift data that is described. So the Hubble tension is a low redshift phenomenon. So it's a local, or perhaps a late time effect. Now, early time solutions to the Hubble test, which we haven't really discussed, but these modify the expansion history prior to recombination. They face at least 7 quite severe difficulties, which have been discussed at length in this review, by someone who actually was advocating early dark energy for some years before being forced to, reconsider based on the evidence. The last thing I wanted to mention, just to recap the other points on here, is basically that very few proposed solutions to the Hubble tension were satisfied like these 2 conditions, which are that, first of all, it wasn't motivated by Hubble tension. People didn't look at it and come up with the idea, because that's always less than ideal, right? But also, the solution should have made a successful a priori prediction of something else. I mean, obviously, it's consistent with the Hubble tension, but it should have predicted something else as well, which we did with the bulk flow curve. There's very few proposed solutions were motivated for some other reason, and also made a successful a priori prediction of something other than the Hubble tension. Yeah, that's where I'd like to leave this. Thank you for listening.
Thank you very much, Indranil.
That's lovely.
So yeah, looking at the time, you maybe have time for one question. I'm curious about one thing. I'm not seeing any hands up. So MOND as a fundamental theory seems quite obviously dead and buried at this point. But is there any hope for using it again as a proxy for some unknown theory in the manner that you've presented?
On a different scale?
Yeah.
Maybe. I mean, people do still try to apply it on galaxy scale sometimes, because ultimately what I was talking about, okay, it's not viable on sub-parsec scales. That's very small compared to a galaxy.
Yeah.
And there are other failures on galaxy cluster scales. Sometimes people apply it on galaxy scales, but yeah, you might be able to, in any kind of scenario where you want to tweak the gravity law for some reason. Sure, you could try to do it using MOND, assuming that the system you're talking about is fairly low acceleration, therefore one would have some effect. Or because you're not necessarily restricted to MOND, you could adjust the acceleration threshold. Sure. Of course, you could come up with almost any equation to do this, but because MOND has had a lot of analytic sort of work behind it already, yeah, you might be able to. But I'm not sure which specific system that would be, but you could try to do that, yes.
Thank you. So if we don't have further questions in the room, is there anything on what?
No, I was just looking at this. I don't think so.
Okay.
I have a technical comment.
Yeah.
Every time it pops up, Kolmogorov Smirnov test. It has very poor rejection power.
So you mean like even if hypothesis is wrong, it might not
I
be.
fail to understand why people use it rather than Anderson Darling, which usually is better.
I think like in this particular case, the referee asked for the KS test. I mean, what I did in my study is look at binomial statistics, because these are relatively small numbers. But yeah, it's not an ideal way of doing it. The way they were doing it is probably even less ideal. They were using like Gaussian statistics, which isn't suited for small numbers.
We can come up with a large number of distributions where Kolmogorov mirror is completely consistent.
Even though
the distribution is definitely the wrong one.
It's definitely the wrong one. So you can like do a pixel by pixel comparison and probably get a binomial likelihood as you were doing. But in any case, the thing I was trying to point out is that, like, regardless of the KS test statistics, it should be clear that you can't really argue the red MOND model is like a massively better fit than the blue Newtonian model. It's actually the opposite way around. Okay, I mean, if you were to,
It's because Kolmogorov-Smirnov also looks at specific shapes of the distribution and not some other features.
yeah, that's right. Like, I mean, for example, like the overall shape of the region here, like, there's not any specific feature we look at, but just sort of, it's less sensitive to the tail.
Because everything you take is a cumulative distribution
Yeah.
function and look at the maximum deviation.
Yeah, exactly. You look at the maximum deviation.
difference.
That's always a bit weird because the maximum deviation is only at one point.
There's lots of features of distributions
Right. Yeah.
where you could have a difference which are not covered.
Yeah, no, this is why I've been arguing for a long time that people should really plot out the whole the distribution and allow readers to like make up their own mind about like, does it look more like the Newtonian model or more like the MOND model? And of course, I think here it should be clear that it looks way more like the blue model, which happens to be Newton.
Probably have become one of my standard comments as a review of why do you use Kolmogorov.
No, this wasn't originally in the review had asked for it, I believe.
Oh, then the review.
I suspect it's just inertia, like everyone knows the KS test where all of it moves forward, I don't know.
What binomial statistics is what you really need for these small numbers.
So if we don't have further questions, I suggest we give Janelle a nice big round of applause.
These things. Everybody.
Wonder I was once on like